Hello friends, welcome to my channel. Let's have a look at problem 1402, reducing dishes. This problem is marked hard by LeetCode, and in this video we're going to give a treatment or share and explain a solution based on elementary math. So first, let's look at the problem requirement. So here a chef has collected data on the satisfaction level of his n dishes. Chef can cook any dish in 1 unit of time. So here the main concept, lag time coefficient of a dish, is defined as the time taken to cook that dish, including previous dishes, multiplied by its satisfaction level. So that is time I times satisfaction I. So we would like to find the maximum sum of the lag time coefficient that the chef can obtain after dishes preparation. So the last paragraph is very important. So here dishes can be prepared in any order, and the chef can discard some dishes to get the maximum value. Here are 3 examples. So the example 2 and example 3 are very straightforward. For example, example 3 contains all negative levels, so we get 0 because we can discard all the dishes to get 0. This is the largest possible. And in example 2, so the levels are all positive, so we can sort, right? So we get 2, 3, 4. Then 2 for finishing 2, we get 2 times multiplied by 1, and then 3 multiplied by 2, and 4 because we need 3 units of time, so it's multiplied by 3. So this way we maximize the lag time coefficient. So in example 1, actually we can check. So if we discard this 2 because there are 2 negative, and then we're going to get -1, 0 to 5. So we have -1 times 1, 0 times 2 plus 5 times 3. So we're going to get 14. So this is the result for example 1. So we're going to into some simple mathematical analysis, so which will yield a very straightforward strategy for this problem. Before we do the analysis, let's first look at the constraints. First, the list satisfaction has a length n, and n is bounded below by 1 and bounded above by 500. So this basically gives us the problem size upper bound. And the last one is also important. So the level, in other words, the satisfaction I, it can be negative, right? So with that said, we are ready to do the analysis. For this problem, for the analysis, we are going to use some simple mathematical formula. So here, we can assume this is capital S is the satisfaction score. So we can order them A1, A2, and AM. First, we would put high levels in the tail and low levels in the head, so that we need more time to prepare the high level dishes. That way we can hope to maximize the lag time coefficient. So this actually corresponds to do a sort. So we can sort S in place when we do the coding. So this is the first part. And the second part is that after sort, we could compute the lag time coefficient if we were to use all the levels in S. So this is nothing but I times AI, then do summation. So here I starts from 1 because the first dish uses 1 unit, 1 time unit. So we get I times AI, summation from I from 1 to n. So this is the initial score if we compute it like this. However, if we pop the lowest level A1, because sometimes it can be negative, then the new coefficient F becomes F bar. So now because the first element is popped, so the A2 is now the first element. So we are going to similarly AI will be the I minus 1 element. So we are going to multiply AI by the time to prepare it, that is I times 1. But now we start from I equals 2 to n, right? because now we have n-1 dishes. So here we would like to compare the f and f hat so that we can get the algorithm or strategy. So if we, this is the expression for f. So if we split I to be I-1 plus 1, so this nothing changes. And then we can split this to be two terms. So one is a summation from I equals 1 to n, so I-1 times ai. And then the other is 1 times ai, to summation. That is the sum of the original s, right, before pop. And then the first item, so when I equals 1, I-1 is 0. So this is nothing different than starting from I equals 2, then up to n. Then times, here is, I guess, I-1, right? Yeah, so basically we get this one, and then plus the sum. So the first one is nothing but f hat, the new lag time coefficient, then plus the sum of s. So this gives us the following observation. So as long as the sum of the original s or the satisfaction score levels is less than 0, so we could continue pop the smallest level to get a larger lag time coefficient f bar, because f bar equals f minus sum of s. So here I will change this to be larger. So this is the strategy we're going to do the coding for this problem. With that said, I guess writing the solution is very straightforward now. Now let's move to the coding part. So for the coding part, what I'm going to do is first we can I changed the satisfaction name to s just for convenience of typing. And then what I'm going to do is to first do a sort, right? So this way, actually, we put larger levels in the larger index, or use corresponding to using longer time. And then because we want to, the smaller one is in the left, we want to pop. So if we use pop 0, it's sort of time consuming. So we can make s to be a deck or queue. So collections deck. So here I'm going to change this type. And then let's use little s as the sum of the satisfaction levels. Then basically we want to get the make the remaining sum of the satisfaction list non-negative. That way we can compute the largest possible lag time coefficient. So this is nothing but a standard while loop. So while s is less than 0 and capital S, in other words, s is not empty, because we want to use some pop operations. Then we're going to increment this s by s pop left, right? So this line actually did two things. First, we pop the smallest level from the capital S, and then typically, because s is less than 0, this element will be negative, and then we use s minus that element. It's called, in effect, we increment the sum, right? So this is the while loop. It's very simple. So if we exit this while loop, there are two possibilities. Either s is already empty, right? So if s is already empty, it means that all the levels in s is negative. Therefore, the largest possible coefficient is 0. Otherwise, we are going to have s is greater than or equal to 0, right? So now let's check the two cases. If not s, so in this case, we are going to return 0. This is the largest possible lag time coefficient we can get. Otherwise, so we are remaining a list or deck s with smaller values in the head and larger in the tail. So we just need to do the return. So we return sum. So here we're going to times the level for I, y in enumerate. So s, the current state of s, but we start from index 1. So this will have the interpretation that the index being time needed to prepare the dish. So this shortcode forms a solution format to this problem. So before we make some modifications, let's first do a check. Yeah, it passes one test case. Now let's look at the generic case. Yeah, it passes all the test cases. So I would say this is one version, because here we use the type conversion, so which is not, we can avoid this if we like. So here we can copy this part. I'm going to change this one to be version v1. And then after I sort, I do not use deck. But here I do the sort in a reverse order. I just need to pay attention when we do the return, right? So we get this, and then we just need to use pop from the tail and the last element. Then same thing here. If not S, we are going to return 0. But now the largest element will be in the beginning of S. So in this case, we need to adjust this, right? We use n minus I times y for y in enumerate. But here the starting index will be 0. So because the first element will be the largest one, it's corresponding to the length, right? So here let me first get the length of this remaining state of S. So, right. So we multiply the largest level by the length, right? So this actually plays the same effect as the first version of solution, but this way we avoided using this type conversion. Also, we just start from index 0. But this is actually a delicate detail when we do the computation. However, as long as we grasp the whole idea, so this is not a problem. Now let's check this solution. Yeah, it passes a test case. Now let's look at the generic case. Yeah, it passes all the generic cases. I guess that's about it for this specific problem. If you find this explanation useful, you can follow me up in my YouTube channel. So with that said, I guess that's about it for this video. Thank you.